Okay, this is our PowerPoint on water supplies, and you should take notes, pause, rewind as you need to. And this is what we're going to go over in this PowerPoint. And, I hope that at this point you realize that the water we drink out of the faucet, or the water you get in bottled water, or even the water you're taking a shower with, it's not just water right out of the ground. It's been treated, and we do that, to make the water safe for people. Here's some of the examples of what we drink. This is a good thing to note that potable water means drinking water. It means that it's safe to drink. Water supplies. Water supplies could be from a lake or from, for instance, an aquifer like Austin uses. Comes into a treatment plant. It's stored in a water tower like we have to the east side of the school, over there by the student parking lot, and then from there it's distributed out. Aquifers, as I said, that's underground water like the Edwards Aquifer. And water is taken out of that through some type of well that takes it out. There's also surface water. We do get some of our water from lakes in Texas. And they do treat it. Take out contaminants, take out bacteria, treat it with chemicals and with chlorine to make it safe to drink. It is put in water towers, which you're familiar with. And this is, for every foot high, it creates 1 pound per square inch. This is 2 different ways that you could have water systems. This might be in a subdivision where you have a main water pipe and then water comes off to each house on each side. Could also be a main water system with water coming off to each business on each side. And then you can also have loops. New pipes and some standard pressures. Residential has some strict code guidelines on what the pressures can be. Commercials could be higher. Head. This is the description, and it's how tall water is in a water pipe. And basically the head tells us how high the water is. Kind of makes sense if you think about like a person standing here, and this is their head up here, how tall they are. The static head, static means something that's not moving or at rest. And it's measured in feet of water, and it's due to the elevation of what we're doing. Have you ever noticed that water towers are always built on a hill? That's because we want the highest point for our water to be stored, so we have all this potential energy as it comes down. So it says here a question, what is the static head at a residential line if the elevated tank is 943 feet and the elevation supply is 890? So at the top up here, 943, down here where we're going to use it, 890. Well, all you do is subtract the 2 heights, and that gives you the static head. See? Pressure is measured in PSI, and we use this conversion right here. So on that last problem, we found 53 feet of water. So to convert it, you just multiply the static head times this conversion factor to get the PSI, to get the pressure. And then it says, is this the pressure you'd get at the faucet in your house or in your shower? Well, and this is the kind of thing we might ask another question. How far above the supply line must we have the water in our tank to get 40 psi, which was the minimum for commercial use? And so you'd use the conversion backwards. This is really 2.31 over 1 psi, and then they just multiply it to get how high. This must be up from not just the bottom here, but if our house is on farther down the hill. This has to be 92 feet above where our house is downhill somewhere over here. We also lose some of our head and pressure as it travels through the pipe. And we call that head loss. And it happens just because of the size of the pipe. There's drag in the pipe. Think like drag on the outside of your car. Fittings, anytime there's an elbow or a T in the pipes, it's going to cut down on it. And also equipment like pumps will cut down on the head. And one of the major ones, as I said, was the drag inside the pipe. The friction as the water tries to go through the pipe makes a big loss. Smaller ones are like the bends. This is our Hazen-Williams formula. It's in your formula chart at the end. And I know these little numbers look funny here, but those are the exponents, and those have been calculated empirically, meaning this isn't a theoretical formula. This is a formula that came up by taking a lot of data and then coming up with this formula that would work. And these are what each of the constants stand for, and we're going to be using these in a minute, so you should write this all down. Okay, so this formula here is on the formula chart I'm going to give you out, and it tells you for different kinds of pipe what a typical range would be for the head loss, or I'm sorry, for the constant C here, and what it would be if we had a new pipe and a typical design value. We don't want to assume that a pipe is going to always be as good as a new pipe, so this is a typical design value we'd use. So the Hazen-Williams formula used for straight pipes, and what we do is we take, when we have a bend, this is an elbow here, we just find an equivalent length. We say this elbow, it gives the same amount of friction as a certain length of pipe. And you have this formula also. And so what we'd say here is, if I have a 45-degree regular elbow, it would be equivalent to different things based on how big the pipe is. So if I have a 10-inch pipe and a 45 regular degree elbow, we'd say that's the same as 9 foot of pipe. If I had a globe valve and a 6-inch pipe, that valve is the same as 190 foot of pipe when we're calculating. So here's a typical problem. 10-inch flange cast iron water supply. So we're talking about cast iron. The pipe between the water tower and the meter includes 7 regular 90-degree elbows, 3 T's, 11 branches, 6 gate valves. What is the equivalent length of pipe? So what we have to do for each one of these items is there's 7 of these, and we look up on the table we just had on the previous page here for what each one of those is. So I'm going to show you one of them, the regular 90-degree elbow. Regular 90-degree elbow, and then we'd look across here to find the right size. We're talking about a 10-inch flanged pipe. So here, 10-inch regular 90-degree elbow is like 14 foot. So you'll notice they put 14 foot right here. Then I need to do 7 times 14 is 98 for all the elbows, and the rest of the table is found the same way. Then we just add up these to get our total equivalent length. So just these pieces in there are equal to 462 feet of pipe when we put them in our straight line calculations. Here's another example. What is a head loss in a 10-inch cast iron pipe, so 10-inch, if the flow rate is 110 gallons per minute, if the pipe is 3.2 miles long, and includes the fittings from the previous slide? So first we have to convert our miles to feet. Here's our standard conversion factor, and we have how long our pipe is. Then we take our actual pipe, here's our actual pipe, plus the number we found for all our fittings on the previous page, add those up to get the total length we're really going to use in our calculation. Here's our formula, our Hazen-Williams formula. We plug that number we just got in for length, and then we have our flow in gallons per minute, our diameter of pipe, and our C value that we had from it being cast iron. Remember, the typical design value from that table was 100. And we just plug that in our calculator. Be sure this bottom part is in parentheses, and you get this number here. That is the head loss. It's as if our tower was almost 3 foot shorter due to the losses inside the pipe. Okay, Dynamic head, this is going to be something, the head of the moving fluid. And we calculate dynamic pressure equals the actual pressure we have. And again, we've got this conversion factor to go from the head to the actual pressure. And we're going to do this example on the next video.